Question 4 introduces an extra bit of complexity by talking about two different kinds of enthalpy change: an enthalpy change of combustion and enthalpy changes of formation. So you have to read the question very carefully to make sure that you don't get all this mixed up. But basically you can see the numbers we're given, the ones that we're going to have to use to calculate our enthalpy changes of formation. So that means the cycle is going to be the same as this kind of thing as we've had in questions 2 and 3, where we link the things on the left hand side with the things on the right hand side via the elements, because we're using the same kind of input data. The point about the enthalpy change of combustion is that's going to provide the overall equation for which we're trying to find the delta H. So that's our starting point. We need to write the equation for that. So we have methanol, CH3OH, plus some oxygen goes to carbon dioxide plus water. So obviously first we've got to balance that. So 1 carbon means 1 CO2, 4 hydrogens altogether means 2 waters, and altogether we've got 2 oxygens plus 2, so 4 oxygens on the right. We need 4 on the left. One of them is already there, so we need 1.5 O2 to make it balance. So that reaction is the reaction which defines delta H of combustion. So delta H for that reaction will be the delta H of combustion, because it's burning 1 mole of methanol. Once we've established that, it's just the same as questions 2 and 3. So because the data we're using are formation data, elements goes at the bottom, and if we go up that way to convert the elements into methanol and oxygen, well, oxygen's still an element, so there's no change there, so we just ignore that term. But we've got to make the methanol, so that's minus 239. On the other hand, if we take that same lot of atoms of the elements, or molecules of the elements, and turn them into CO2 and water, making 1 mole of CO2, so that's minus 394. And we're making 2 moles of water, so that's minus 286 times 2. Okay, always be careful, use the balancing numbers, and just explain to yourself that we're making 2 moles of water, therefore it's 2 times the delta H of formation. And if you add that lot up together, that gives you minus 966 on that side. So then, as before, we invoke Hess's law and say, right, what we want is this number, and that's the same as going down here and then up there. The sum of those 2 steps will equal that one. First one is the opposite of this, so that's plus 239, because we're going the wrong way. That brings us down to here, and then coming up to there, well, that's the same as that, so that's minus 966. So we get our answer, which is that delta H of combustion is equal to minus 239, so plus 239, because we're going that way, minus 966, which comes to minus 727 kilojoules per mole. First part of question 5 is asking about, why we're bothering with all this Hess's law stuff, really. Why should you bother with these cycles? And the answer is because often it's really quite difficult to measure delta H for an individual reaction. I mean, it's always quite difficult because you have to take so many precautions. If you're doing an MC delta T type experiment, you have to take so many precautions to, to take account of heat losses and all that kind of stuff. But sometimes it's more than that. Sometimes it's the fact that it's very difficult to measure delta H for a specific reaction. So the one it wants here is formation of carbon monoxide. So the reaction would be this: carbon solid plus a half O2 gas gives you carbon monoxide gas. And that's going to be extraordinarily difficult to measure the delta H for, because of course there's going to be a competing reaction, which is that carbon could react with a whole mole of oxygen to give you CO2. And trying to control it so that you only get this reaction and none of the carbon gets converted to CO2, that's going to be extraordinarily difficult. You can see that if you get incomplete combustion, you're likely to get a mixture, but making sure you only get this one, that's going to be really hard. So Hess's law gives you a way to measure delta H for that reaction without actually having to do the experiment, and that's what the point of the whole thing is. So the answer to the question is, or at least probably the best answer to the question is, that it would be very difficult to control the conditions so that carbon reacted with oxygen only to produce carbon monoxide. You would tend to get a mixture with CO2 as well, and so the delta H wouldn't refer purely to that reaction. So part B asks us to use Hess's law to calculate delta H of formation of carbon monoxide. So we can write down the equation for that, because it's carbon in its normal state, which would be solid graphite or possibly diamond, but graphite's actually the most stable state, plus a half O2, which is a gas, gives you carbon monoxide gas. So that's the reaction which is going to give us delta H of formation of carbon monoxide. But the data we're using this time are different, because they are delta H of combustion. Okay, that's what that C stands for. And delta H of combustion means that we can apply Hess's law in the same kind of way, but our cycle's going to look different, because the data we're using are not formation data, so we don't have elements at the bottom. Because we've got delta H of combustion, what goes at the bottom, the link between the two sides of the equation, are the products of combustion. And of course, when you burn carbon, if you burn it completely, which, if you remember the definition, is enthalpy of change of combustion is when you burn 1 mole of a compound completely in oxygen, so carbon will oxidize all the way to CO2, and carbon monoxide also will oxidize to CO2. So what goes down at the bottom here are the products of combustion, which in the case of these compounds is just CO2. More commonly, where you've got organic compounds, it will be CO2 and water, and occasionally other things as well, but products of combustion here would be CO2. So we put the data on here. So again, what you have to do is think, what is combustion? It's the process when you burn carbon and it turns into CO2. So that number refers to going this way. Okay, because you're burning carbon, you're turning it into CO2. That's what combustion is. So the arrow goes that way. So for carbon, delta H of combustion is minus 394. So that means if we take 1 mole of carbon and it burns completely to turn into CO2, so going that way, delta H is minus 394 kilojoules per mole. On the other hand, if we take a mole of carbon monoxide and it burns in oxygen, reacts with an extra oxygen to turn into CO2, that's going that way, that's delta H of combustion, and that's minus 283 kilojoules per mole. Now you might object and say, yeah, this doesn't really balance, because, you know, what about this extra oxygen that's coming in? And you can get around that if you really want to make everything balance, by saying, right, you need an extra half O2 coming in here and an extra half O2 coming in here to make those equations balance. But you can see it's one of those things that's not going to affect the calculation, because you're just feeding in a half O2 on each side. So when you do this, which is what we're going to do, you put half O2 in, you get half O2 out again. So normally people don't bother, but if it upsets you that this oxygen's apparently appearing from nowhere, then that's fair enough, and you can feed it in like that as well and say, right, to get down there you need an extra half O2, you need an extra half O2. But when you put together your indirect route, you'll realise that that kind of disappears in the noise. So in most of these examples I'm not going to bother doing that, because it just clutters up the working, and so long as you can see why it doesn't matter, then it's easier just to leave it out. Okay, so then we're ready to invoke Hess's law. So you're getting used to this by now, hopefully. That's the delta H we're interested in, and it is the sum of those two steps going like that. So the first one is going the same way as that one, right, because we're burning the carbon, turning it into CO2. So we get that delta H, the enthalpy of formation of CO, is equal to minus 394 going that way. But then we come back up here and that's the opposite of that one. It's going the wrong way, so the sign changes. So it's not minus 283, it's plus 283, which is minus 111 kilojoules per mole. And that's the answer to the question. Okay, so 6 is another question where you've got to read it carefully, make absolutely sure you think it through, because it's mixing up two different kinds of enthalpy change again. The data you're given are enthalpy changes of combustion, but what you're being asked to calculate is the delta H of formation of ethanol. So you've got to make sure you don't get it all mixed up, and you think, right, what I want to calculate is delta H of formation of ethanol. So my equation across the top of my cycle is going to be forming 1 mole of ethanol, which is C2H5OH liquid, from its elements. So that's 2 moles of carbon, which is a solid because it's like graphite. We've got 6 hydrogens on the right, so that's 3 lots of H2. And we've got 1 oxygen, so that's half an O2. Okay, so that's the reaction for forming 1 mole of ethanol from its elements, and that's what we need, because that reaction, the delta H is delta H of formation of ethanol, which is what we want to find. But the data we're using are combustion data, and we know now that when we calculate things using combustion data, what goes down at the bottom are the combustion products, which, because we're talking now about burning not just carbon but hydrogen as well, either separately or in the form of an organic compound, that's going to be CO2 and water. Now we could balance that up and work out how many moles of CO2 and water, but again, it doesn't actually affect the calculation, because what we make in the first step we destroy in the second step, so it doesn't actually matter. So it's easier just not to bother and just write that. So let's put the numbers in. We're going to have a reaction going that way, because combustion is when you take these substances and they burn and they turn into CO2 and water. So you shouldn't be guessing the direction of the arrows, you should just be asking yourself, what does combustion mean? And combustion means taking the elements and they burn and they turn into, so they go that way, turn into CO2 and water. So we've got 2 moles of carbon, so that's minus 394 times 2. Okay, don't forget to use the balancing numbers like that. And we're burning 3 moles of hydrogen, so that's minus 286 times 3. So we've got to add all that lot up, which gives you minus 1646 kilojoules per mole altogether going that way. If we go this way and just take a mole of ethanol and turn it into those same combustion products, that's just delta H of combustion, so that's minus 1400 going that way. So Hess's law says that delta H of formation, which is this, is numerically the same if we do it in 2 steps like that. So we take the elements, we burn them to make CO2 and water, and then we unburn the CO2 and water and turn it into ethanol. Doing it in 2 steps gives you the same overall delta H as 1 step. First step is the same as that one. You can see the arrows are going the same way, so it's exactly the same. Sign doesn't change. So that's minus 1646. But the second leg coming up here is the opposite of this one. So if it's minus 1400 burning a mole of ethanol, it's going to be plus 1400 going the other way and recreating a mole of ethanol. So plus 1400. And that then means that we can easily calculate our answer. So delta H of formation of ethanol is equal to minus 1646 plus 1400, which is minus 246 kilojoules per mole. Is the right answer. Question 7 has a quite scary looking equation, but again, actually it's just a straightforward case of using the enthalpy changes of formation. Remember, that's where you start. You look at the numbers you're being given to do the calculation, and you see their enthalpy changes of formation, and you think, right, if that's what I've got to deal with, then I'm going to construct a cycle that's based on having elements in the middle here, because those data relate to turning the elements into the compounds. Okay, so if we deal with the left hand side first, if we take those elements, we're not going to worry about balancing it up and saying what they are, we'll just write elements, and if we take those and we turn them into those things on the left hand side, we've got 4 moles of this compound, which is called methylhydrazine, so it's plus 53 times 4, so we've got 4 moles of that, and we're making 5 moles of N2O4, so it's minus 20 times 5. Okay, so you can see, as we've mentioned before, that delta H of formation is sometimes positive, sometimes negative. It depends on the strength of the bonds you're forming in the compound compared to the ones you have to break in the element. So if you crunch all those numbers together, you get plus 112 kilojoules per mole to form those compounds from the elements. On the other hand, if you take those same elements and go this way, you're making 4 moles of CO2, so that's minus 394 times 4. Making 12 moles of water, so that's minus 286 times 12. And the nitrogen, of course, is unchanged, because nitrogen is an element, you're making it from the elements, so nothing's happened, and therefore that makes no contribution. So if you add that lot up, that comes to minus 5008. Okay, and then Hess's law comes into play. This is what we're trying to calculate. This is our indirect route that corresponds to that change, going from left to right. So the left hand side is the reverse of forming those compounds, because you're unforming them, turning them back into the elements. So we get delta H of reaction. First leg is minus 112. Okay, because it's minus 112 if we're coming back down this way. Second leg is exactly the same as that one. Right, we're going the same direction, so it's same sign, so that's minus 5008. So it's minus 112 minus 5008, which is minus 5120 kilojoules per mole. And that's actually another one of those rocket fuel calculations. This is another rocket fuel mixture, because again you can see, first of all, it's very exothermic, lots of heat, lots of expansion of the gases, lots of thrust, but also you're taking liquid propellants, because both of these compounds, if you cool them slightly, are liquids. And so they take up very little volume, but when you turn them into gases, huge expansion of volume, so lots of stuff got to shoot out of the nozzle of the rocket. But the important bit is that's the number